Our past contains an unsolvable paradox that's riddled scientists for decades. To this day, no one has been able to explain how one unremarkable planet in an arm of the Milky Way became home for life. According to a new article published in the Nature Communications Journal in the spring of 2022, all organic elements needed to form the first living molecules were brought to ancient Earth with special carbonaceous meteorites. But even this doesn't explain how separate inert fragments, that is, basically nothing, formed into extremely complex DNA structures. And if we dig deeper into our universe's past, we'll find even more paradoxes of this kind. If we put them all together, it'll turn out that it's not only us who shouldn't exist. There should either be no Earth as it is now, or our galaxy, or even the universe itself. This brings us to the main question. How come the world as we know it formed from pretty much nothing? Our entire solar system should not have formed into what it is now. That includes Earth. Although the European Space Agency, which is NASA's counterpart, suggests that our home is not one planet, but rather the Earth-Moon system. The Moon has an enormous influence on all the processes on Earth because it's abnormally large. Only Ganymede, Titan, and Callisto are bigger than the Moon. But after all, they orbit the colossal gas giants Saturn and Jupiter. And while the origin of their moons is easy to explain, the Moon's appearance in Earth's sky is still a mystery without a conclusive answer. One way or another, it all comes down to the giant impact hypothesis. 4.5 billion years ago, a Mars-sized planet called Theia collided with Earth at a low speed, and the ejecta, which chipped off both bodies, formed the Moon. But how exactly did that happen? One of NASA's most recent supercomputer simulations revealed that it might have happened within hours. In it, Theia's initial impact led to the formation of 3 celestial objects at once, but a more massive satellite fell back to Earth, pushing the young Moon into a stable orbit. So it just formed in a single day and had the same size as now to boot. But here's the rub. Whenever astronauts took lunar soil samples, they never found rocks that differed from those on Earth. Does this mean that none of the millions of Theia's fragments, which flew everywhere upon the collision, landed on the Moon? How is that even possible? In an attempt to explain this and other oddities, Dutch astronomers Robert de Meyer and Wim van Westerinen proposed a nuclear explosion hypothesis. You probably imagined young Earth bombed by some powerful cosmic civilization. But what these two scientists have assumed is even more curious. Earth's crust famously has an abundance of radioactive elements, mostly uranium and thorium. De Meyer and van Westerinen suggest that they were so ample in the still molten and shaping Earth that at some point they just reacted with each other and boom, an explosion much more powerful than any of today's nuclear arsenals forced out a piece of Earth that eventually became the Moon. I don't think you'll be surprised when I say that this theory also has flaws and doesn't explain the parameters of the Moon's orbit. All in all, our Moon is so strange that sometimes it feels like it just came out of nothing. But the solar system is even weirder than that. You're well familiar with this space map in my videos. 4 small rocky planets, including Earth, followed by 4 gas giants. However, a similar distribution of exoplanets orbiting other stars has yet to be found. For example, all the planets in the TRAPPIST-1 system are pretty much Earth-sized. Why do ours differ so much then? As a matter of fact, most of the planets discovered in other star systems are much larger than Earth. They're referred to as super-Earths. Moreover, most systems with sun-like stars have all the planet orbits tightly packed around where we only have Mercury. So, anomalous as it is, how did our solar system form at all? The standard theory is that around 4,600,000,000 years ago, in place of the solar system, there was this protoplanetary disk. And all the oddities that manifested later are usually explained by Jupiter. It's said to have swept through the orbits like a hurricane, pulled the asteroid belt, which would have otherwise made Earth, Mars, and Venus more massive, and pushed other planets away to where they are now. However, simulations reveal that this version just doesn't hold water. So, in 2022, astrophysicist Rajdeep Dasgupta and Andre Isidoro suggested an alternative model in which the solar system's protoplanetary disk was more like Saturn's rings. These gaps adequately explain most of its oddities, but cause a new headache. You see, the solar system's protoplanetary disk itself formed from a cloud of interstellar dust and gas. If you'd found yourself inside it 5 billion years ago, you would have hardly seen any matter around. A few atoms per cubic meter. That's practically nothing. Scientists believe that over millions of years, this rarefied cloud was clumping together in the blast waves from around 20 supernovas nearby. However, forming such a distinctive disk out of rings would require a completely out-of-the-ordinary combination of external impulses. And if the true origins of the solar system are still a mystery, just imagine what the deal is with the universe's larger objects. The origins of myriads of galaxies scattered around the night sky have been a perpetual puzzle for astronomers. When, in the 1930s, Edwin Hubble calculated the parameters of this bright elliptical galaxy in the Virgo constellation, he thought he had made a mistake. The results suggested that the trillions of stars in it formed a sphere with a diameter of 5.5 million light-years. It turned out there was no mistake. This enormous galaxy is indeed dozens of times larger than either the Milky Way or our neighbor Andromeda. But how could such a monster form at all? Edwin Hubble believed that such galaxies with the primitive elliptical structure were the oldest in the universe. After all, their stars are, among other things, the oldest and the dimmest too. On the other hand, the more refined spiral galaxies studded with new stars, like the Milky Way, seemed to the astronomers the youngest. So far, so good, logic-wise. However, trying to confirm this conclusion, Hubble's followers ended up with paradoxical data. Most spiral galaxies turned out to be as old as 12 to 13 billion years. In other words, almost the same age as the universe itself. While the elliptical galaxies seemed to be no older than 10 billion years, and some were as many as 3 times younger than that. At first, this mystery baffled astronomers, but then they marked interacting spiral galaxies like these two. We see them as they were 9 billion years ago. The bright tail in the photo is a gas jet, which could have formed 10,000 suns if not for the catastrophic galaxy merger that pushed it out. So it should result in no other than the dim and shriveled elliptical galaxy, although still younger than the original spiral galaxies. But in this case, where did these two come from? This bright globular cluster of 150,000 stars, Messier 2, amazed astronomers when they found out its age. It's at least 13 billion years old. The number sounds familiar, doesn't it? Apparently, it's a miraculously surviving ancestor of spiral galaxies. As the theory goes, just a billion years after the Big Bang, such star clusters began colliding with each other, forming more and more massive objects. NASA's supercomputer simulations revealed that because of the way interstellar gas behaves, any such globe is bound to turn into a disk-like structure with spiral arms. And at the beginning of 2023, the James Webb Space Telescope brilliantly confirmed this theory with the photo of the 9 billion-year-old Sparkler protogalaxy, which is forming globular clusters into a disk right before our eyes. But while searching for confirmation of galaxy evolution theories in the young universe, scientists stumbled across something that actually casts doubt on them. In its first year, James Webb captured dozens of the most ancient galaxies with their formed disks. Good job, you'll say. Well, that good job gives astronomers a headache. You see, these galaxies appeared somewhere between 200 and 400 million years after the Big Bang. But isn't that way too early for galaxies to have disks? And every time things don't add up in the galaxy evolution theory, scientists resort to their favorite method. They blame everything on invisible dark matter. It almost doesn't interact with ordinary matter, and if you ended up inside a clump of dark matter, you wouldn't see anything at all. However, for their math to add up, scientists need its amount to be 5 times larger than the number of observable stars in galaxies. This method has already helped astrophysicists explain why galaxies spin too fast. Without an external restraining force, their arms would have blown across space long ago. Modern science considers this force to be massive halos of dark matter, often many times larger than the observable galaxies. But within the first hundreds of millions of years after the Big Bang, dark matter was nothing more than just detached clumps around primordial star clusters. And this invisible nothing served as the cement in the foundation for galaxies. In fact, NASA simulations can only produce something similar to the modern-day universe if large masses of dark matter are included in them. It might be that in the first hundreds of millions of years, its properties were somewhat different, and that's what made it possible for galactic disks to form earlier than scientists anticipated. But by making dark matter a mandatory ingredient in galaxy evolution, they ended up in another trap. Right now, 8 dwarf galaxies are orbiting the Milky Way. Essentially, these are grown globular clusters that still haven't been swallowed by our galaxy since the days of our universe's youth. But there are supposed to be many more of them. All simulations with dark matter inevitably show not dozens, but hundreds of such satellites bound to any large galaxy. And this contradiction is so glaring that astronomers even gave it a name. And so far, the dwarf galaxy problem doesn't seem to have a solution. And here's the cherry on top. When astronomers identified the mass of ancient globular clusters, it was overall consistent with the masses of stars making them up. This means they contain almost no dark matter, which is supposed to be there according to the galaxy formation theories. But what's even more baffling to scientists is the origin of the universe's most extreme objects. How come there are so many supermassive black holes in space? When in 1964, astronomers spotted the compact and almost invisible object Cygnus X1 with a mass of 20 suns, that discovery alone was enough for them to reconsider the star evolution theories. Before that, it was accepted that when they die, mass stars leave behind neutron stars with a mass of no more than 2.5 suns. But it turned out that especially large celestial bodies like blue supergiants collapse into black holes, whose mass can vary from several to dozens of solar masses. But 10 years later, the discovery of Cygnus X1 was followed by the discovery of an object called Sagittarius A star at the galactic center of the Milky Way. When the math was done, it was concluded that it had to have a mass of over 4 million suns. Such a supermassive black hole is too hefty to have formed from any star. Cue the galaxy evolution theory. In the early universe's dense globular clusters, normal black holes with the same mass as stars could merge multiple times, joining one another when forming galaxies from those same clusters. And that's how, several billion years later, we ended up with one supermassive Sagittarius A star at the center of the Milky Way. except that when we gave it a closer look, our black hole turned out to be really teeny tiny. Just recently, astronomers discovered a supermassive black hole at the center of a faraway galaxy. It was 400 times as massive as ours, with a mass of over 1.5 billion suns. An object like this might well have been formed after two spiral galaxies merged several billion years ago, except this black hole is the oldest one ever discovered. It's 13 billion years old, which means it somehow gained a colossal mass in just 800 million years after the Big Bang. And there were hundreds, if not thousands, of such supermassive monsters in the early universe. So how could they come into existence so early at all? One of the possible explanations assumes that stars at the dawn of the universe weren't at all what they are now. The Sun is considered to be a population 1 star, which formed from the remnants of more massive stars belonging to population 2. Their remnants also make up ancient galactic centers and globular clusters, but over time, astronomers realized that even older and more massive population 3 stars must have existed in the early universe too. They formed just 100 or 200 million years after the Big Bang from primordial gas clouds and clumps of dark matter, when the universe was much denser. They're assumed to have consisted only of hydrogen and helium and have a mass that was 1,000, if not 10,000 times more than the Sun's. Such infernal fireboxes would have burned all their fuel in just 2 or 3 million years, leaving black holes with corresponding masses after their deaths. And one of the wildest theories suggests that those black holes were born right inside their host stars, while the latter ones were still alive. These mysterious objects of the early universe are known as quasi-stars because their masses were so much bigger than today's record holders, like Stephenson 218, that their hydrogen atoms in their cores were under too much pressure, making normal nuclear reactions impossible. Instead, the center of a quasi-star would almost instantly collapse into a small black hole. But paradoxical as it may sound, that didn't kill it. We're used to the idea that black holes just suck everything into them in the blink of an eye, but even they have their limits. No, in truth, matter doesn't go straight into a black hole. It first curves into an accretion disk, which feeds the monster bit by bit. So a black hole at the center of a giant star just couldn't gobble up all its matter at once. Instead, it formed an accretion disk and started sort of drinking the star through a straw. Over hundreds of thousands of years of this force feeding, the black hole destroyed its host from the inside for good, and then broke out looking for new prey. According to some calculations, quasi-stars could be as massive as 1 million suns, which means the first supermassive black holes appeared just over 100 million years after the Big Bang. But here's the rub. Astronomers haven't discovered a single population 3 star yet, not even a normal one. Even with the Webb telescope at hand, it's extremely hard to peer into the depths of the universe and spot such a thin layer of just a couple million years when they existed. But scientists have a workaround. They can study the very beginning of the universe so thoroughly as to use it as a basis for determining everything else through calculations and simulations. And that's where science is really at a loss. The dawn of the universe offers us the main mysteries of all of existence. It literally might have formed out of nothing. But how is that possible? The cosmic microwave background permeates all space in the radio range. But as a matter of fact, it's the universe's very first light, emitted at around 380,000 years after the Big Bang. It came from primordial hydrogen atoms, which eventually formed the giant population 3 stars. But then, where did the atoms themselves come from? How did matter emerge from the pure energy of the Big Bang? Alas, the cosmic microwave background is an impenetrable barrier that keeps the solution away from the most sensitive telescopes. You see, before it emitted light for the first time, the universe consisted of opaque plasma, somewhat similar to that raging under the surface of stars, but much more rarefied. Only science can see as far as that time. But that plasma led us to one of the biggest mysteries of the young universe, because it's not just ordinary matter that existed in it. In 1932, physicists synthesized an anomalous electron with a positive charge for the first time. It was an anti-electron, better known as a positron. In 1955, they managed to synthesize an antiproton. And in 1995, scientists at the Large Hadron Collider brought to life as many as 9 antihydrogen atoms consisting of positrons and antiprotons. But as soon as they collided with protons, all that was left of all the atoms was a flash of gamma rays. The uncontrollable annihilation upon contact with ordinary matter hasn't allowed scientists to synthesize even a gram of antimatter yet. But antimatter was everywhere when the universe was younger than 1 second. Moreover, there were as many particles as antiparticles. They kept forming in a high-energy environment and then colliding, annihilating, and turning into energy again. In theory, when the universe expanded and cooled enough, they could have flown away from each other far enough and formed stars and anti-stars, which in turn would make up galaxies and anti-galaxies. It would be impossible to tell them apart from a distance, as both would emit ordinary photons of light. The theory is so convincing that astronomers regularly scan space for excess gamma radiation produced by particle collisions at the borders of matter and antimatter domains. However, no anomalies have been detected so far, which means that, at least the universe we observe, entirely consists of ordinary matter. But if it wasn't formed from primordial energy coupled with antimatter, it means that it had to appear out of nothing. Physicists are unhappy with this theory, so they keep coming up with new explanations, some of which sound quite fantastic. In 2022, a research team at the University of Waterloo proposed a rather extraordinary universe-anti-universe model, in which both of them were the result of the same Big Bang. Think of them as 2 soap bubbles growing from the same ring to opposite sides. The good news is that the universe-anti-universe model generates plenty of dark matter, which we must work on in our galaxy evolution theories. But at the same time, such an early separation of matter and antimatter means that the young universe wasn't supposed to survive an ultra-short period of extremely rapid expansion, which cosmologists call cosmic inflation. And the problem is that it's crucial for explaining many other features of the universe, particularly its incredibly flat space without global curves. Besides, the dual model is practically impossible to confirm experimentally. We can't just zoom out and see the anti-universe's bubble on the other side of our universe. Most modern-day physicists reject this model. Instead, they suppose that in the first 10,000ths of a second after the universe was born, an unknown quantum phenomenon destroyed part of the antimatter, which left enough non-annihilated matter to form space as we know it. But even if and when scientists find out what that phenomenon was, they'll still have the central mystery to uncover: what triggered the Big Bang itself? Modern-day physics can describe the development of the universe more or less in detail, up to 10 to the minus 43 seconds. This time span compares to 1 second, pretty much as 1 proton compares to the observable universe. That may sound close enough to the Big Bang to unravel the mystery of its nature, but that single moment is where all of our physical theories break. The universe back then was of a subatomic size, and in normal conditions, we'd apply quantum physics to it. But you see, this is not about one single particle, but all the particles that can exist in our world packed into a minuscule container. container. They were all subjected to primordial gravity. But here's the thing. While we have no problem applying it to stellar systems and galaxies, we have no idea how it works on a quantum scale. If you dare try applying Einstein's relativity theory equations to individual particles, you'll end up with infinite masses and energies. Still, quantum physics may actually hold the key to the nature of the Big Bang. In 1973, American physicist Edward Tryon published an article that stirred academia. His question was, is the universe a quantum fluctuation? This is the name given to spontaneous bursts of energy that happen at the subatomic level of completely empty space and immediately turn into nothing. They don't violate the law of conservation of energy because they take place for a very short time. It's like they borrow energy and give it back in less than 10 to the minus 43 seconds. That's one curious coincidence with the least studied era of the early universe, wouldn't you say? In 2014, scientists from the Wuhan Institute mathematically proved that spontaneous quantum fluctuations in a large enough space might have failed to dissipate and did the opposite, which is begin to expand exponentially. In other words, the Big Bang, and then the entire universe, could indeed arise from nothing, rendering the question of what caused it pointless. Everything we see around us, planets, stars, galaxies, is just an incident that spiraled out of control. As if the theory of the universe coming out of nothing weren't mind-blowing enough, the Nobel laureate Roger Penrose went as far as to propose a hypothesis according to which the Big Bang-inducing quantum fluctuations happened nowhere else than in the previous universe. He noticed that the equations describing the first moments of our universe are surprisingly similar to the ones that could describe one of the possible paths it might take in the future, the so-called heat death. This heat death may come trillions of years from now, when not only stars and galaxies will have died and dispersed, but even black holes will have evaporated, with only individual quantum particles of residual radiation roaming through cold space. Time in this age will seem to freeze because no one will be there to measure it, and every subsequent moment won't be much different from the previous one. There was no time at the moment of the Big Bang either. So what if these two conditions are linked? Just imagine, the cold, dead universe is shaken by a spontaneous fluctuation of a new Big Bang, and everything starts over. Doesn't it sound very much like the myths and legends of many cultures about the continuous cycle of the world's destruction and rebirth? And because it might have happened an infinite number of times, we'll never be able to get to the very beginning, provided, of course, that there was a beginning in the first place. So what do you think? Do we live in the first universe or in one of many?
Do you love listening to random people's opinions on important topics? Why don't you try and listen to this absurd person?
If we're not living inside a simulation, how come space looks exactly like what I see when I close my eyes?
This guy is just as unqualified.
I worked as a male model for a brand that sells sacks of potatoes.
Dangerously confident.
If it's about this size, I think I can punch that dog.
And eager to fix things that no one asked him to.
I know it might sound radical, but I think we should sell the economy.
How to fix YouTube comedy channel. Don't worry, this dude actually only talks about movies and TV shows.
Why won't they make a live-action remake of the moon landing?